So hello, I'm Xavier Boutier. I'm a PhD student at Mila. I'm also a full-time research developer at Mila in the IDT teams, the Innovation, Development and Technology. We're developing tools or software and also maintaining computational infrastructure for the researcher at Mila. And so for the question, Mila is a research institute. It's combining professors from different universities. I've lost track of the number of professors. Now I think it's more than 20 or 30. It's 4 or 5 different universities in Montreal. And now I think we are more than 500 students and researchers, so PhD students mostly and master students. And yeah, so I've been working on Orion at Mila since about 3 years now, and we're collaborating with IBM since a year. And Young-Ang will talk more about this collaboration at the end of the presentation.
Okay, let's move to the next chart. Here's the agenda. Xavier from Mila will start with HPO best practice in real-world setting. Xavier himself is a deep learning researcher and the creator of Orion. I think there's no better person than him for this topic. He will talk about the search space design, algorithm selection, experiment execution with version control and visualization. Then he will introduce Orion. This is an open source HPO framework. After that, I will talk about Mila and IBM collaboration and our focus area. We have been working together for the past year. I would love to share some of the exciting work from our teams. I will hand over to Xavier.
Thank you, Young-Ang. All right, so let's start from the beginning. What is hyperparameter optimization? So we have this robot or an algorithm that is able to learn to solve some task. Okay, it's able to learn thanks to its electronic brain or the neurons in a neural network, let's say. But it's not able to learn any task, and so there's some knobs on the robot that makes it possible to adjust how it's learning, and so that it can learn maybe some tasks better than others. These are the hyperparameters. So if we're thinking about a neural network, that would be, let's say, the size of the layers or the learning rate of the optimizer. That's what we call the hyperparameters, in comparison to the parameters that are the neurons that are being adjusted when we're learning. And hyperparameter is very important. There's more and more work showing the importance of hyperparameters. The examples that I give here are papers where they show that if you give enough budget for the hyperparameterization of the baselines, you can actually increase their performance up to what have been considered SOTA at the time of these different publications. So it's very important to invest at least a reasonable amount of resources on this process. So the typical steps of the hyperparameterization is that first we design the search space. So we decide what are the hyperparameters that we want to optimize, because there are so many. Often we do not optimize all of them. We decide also the different values that they can take and we want to try out. After that, we choose the algorithm. This may seem like a trivial step, but it can be a tricky one. Sometimes you may choose an algorithm that is actually not performing well for the given task you have. So I'll discuss this. And then I'll give a few tips for when you run the experiments, when you do the hyperparameterization. And then we can visualize the results to try to analyze the performance to see if we manage to find good hyperparameters. And I'll discuss another step that is not so common, which is just a feedback loop. So an adjustment of the design based on the visualization. We redesign the search space, maybe change the choice of the algorithm, and then run again the hyperparameterization for further steps. So first of all, search space design. There's different type of hyperparameters. I'll discuss the different types as I go over typical hyperparameters and also give tips on different values and how to try to optimize them. This is based on the literature, based on my personal experience, and also based on the experience I have with the students that comes to me to ask questions for the hyperparameterization. So first type of dimensions, there's the continuous one. Most popular example is the learning rate. So most of the time you have the learning rate that you want to optimize if you're working on deep learning. This hyperparameters changes affects the objective in a logarithmic scale. So you want to search in a logarithmic scale. So I give here this example of a prior that I call, which is the space in which you try different values for a hyperparameter. So this prior is a log uniform from the value 0.001 to 0.5. This is an example of a good starting point to optimize the learning rate. One of my tip here is to not avoid large learning rates. Often people try smaller learning rates and they avoid the larger one because they think it will just make the optimization unstable. But with most modern neural network architecture, the large learning rates are actually good values as a starting point if you combine this with the learning rate schedule. And so the next continuous dimension that I give as an example is the learning rate schedule. It can be not continuous if it's a learning rate schedule that is by step, okay? But if you think of an exponential schedule with a gamma, which is the rate at which the learning rate is decaying, this is a continuous dimension. And this is a very important one that often I don't see it being optimized to keep it fixed. Because it makes the stochastic gradient descent competitive against most other optimizer. And also in the work of Wilson et al. By the way, all the references that you see here are listed at the end of the slides that I will share with you. So you can have access to all of these papers and read them if you're interested. And so as I've been shown by Wilson et al., adjusting the learning rate schedule and giving enough budget for a good adjustment of it makes SGD competitive to most other optimizer and even can make it outperform them in terms of generalization. So it's very important hyperparameter. The gamma can be a bit tricky to optimize because the way it affects the objective is as you get closer to 1, it has more and more effect. So if you just use a logarithmic scale, it will not work very well. What I recommend is to use this scale here, which is a transformation of the log uniform. So you take the log uniform from 10 to 10,000, and then you set gamma, the decaying rate, the learning rate, to n-1 divided by n. This gives you a space. For instance, if you take 5 equally spaced points on the space, you will have 0.9, 0.99, and so on. So as you go along the space, you're kind of adding more decibels to the precision of the gamma. And this is a good way to set the prior for the learning rate schedule if you want to optimize it. Another hyperparameter that we often see is the momentum. It does not very much affect the generalization. It's more about the training time. So it may make your training a bit more faster. So if you are in a case where you don't have time to train your model until convergence, it may be good to try to optimize the momentum. But if you have time to let it train until convergence all the time, then it's maybe better to just fix it and avoid this one to make the optimization easier. And then finally, another continuous dimension is the weight decay. Most of the time we think of it as a regularization. So we try smaller values because we think that if it's too large, it will handicap the neural network because it will be too strong regularization. But this is a bit tricky because when you're using batch norm, which is fairly common in modern neural architecture, the weight decay is not anymore a regularization, but it has the effect of an adaptive schedule on the learning rate. You can read the paper of Hoven and Ofer on the topic. And so in this case, it's worth trying surprisingly large values, I would say, for the weight decay. So depending on the architecture you have, you should try large values for the weight decay. So something like that. No, 0.01, something like that. Okay, so that's for the continuous dimensions. Then there's the discrete dimensions, so they're integers, basically. One that I often see when students come to see me is the batch size. So they try to optimize the batch size. I do not recommend optimizing it. I would say the best strategy is to just increasing it until you fill the memory of your GPU to make sure that you're using your GPU to its full potential, and just keep it fixed. And another reason also to not optimize it is that there is a strong relation between the learning rate and the batch size and how it affects the generalization of a neural network. And as has been shown in this paper, there's it's the ratio that is important between the learning rate and batch size. So again, if you just keep the batch size fixed, it makes it easier for the optimizer to optimize, because otherwise you would need to keep track of the two hyperparameter and optimize them together. So it's a lot better to just, increasing it until you feel the GPU, and then you keep it fixed and you optimize just the learning rate, not the batch size. Another one is the size of the layers. This can be tricky because as you increase the size of the layer, you can make training a lot much slower because it becomes more expensive. And so if you're running a large-scale hyperparameter optimization, you can quickly kind of lose control of your optimization because some of the trial takes an eternity to complete. So in this case, it's good to do an early stopping, not in terms of the number of epochs, but instead in terms of a wall clock time, to make sure that some of the trials are not taking too much time to train. And also it can be tricky in terms of the memory, because if you're not careful enough, some of the hyperparameters value for the size of the layer would just blow up the memory of the GPU. Another discrete dimension is the number of layers, and this one can be even more trickier because again, the memory usage will increase quickly, and also if you use it in combination with the size of the layers, if you try to optimize both at the same time, you have this issue even worse. So what I would recommend, if you have the number of layers and size of the layers that you want to optimize, you should look into specifically neural architecture search algorithms, not general hyperparameter optimization. And you can take a look at the book of Utter et al. On AutoML, or the great paper of Liam Lee, which discuss about architecture search. So finally, the different type of dimensions are the categorical ones. So there's no, let's say, ordinality between the values. It's not like real U is something that comes before sigmoid or whatever. It's just a random list. And so this is an example, by the way, of how you would define choices. So a categorical dimension in Orion. And in this example, that's the activation function that you want to choose. So it might be a real U, it might be a sigmoid, a tanh Swift. I don't have specific recommendations for this. From experience, most of the time, real U would be one that would work well. Swift maybe as well. I've seen many times people wanting to optimize the type of optimizer. So either if it's SGD or ADAM or ADAGRAD, and make this a hyperparameter. And now, with each of them, there's different hyperparameters, right? There's the beta 1 and 2 for ADAM. There's not this for SGD. And also even the learning rate that is coming across them, it's the same name, but it's not the same kind of values you would want to have for the different ones. So these hyperparameters are conditional on the type of optimizer you're using. That's why we're calling it conditional hyperparameters. So I would say there's two scenarios in this case. If you're only optimizing the type of optimizers and their hyperparameters, so there's not a hyperparameter like the size of the layers that is common to all of them, the best strategy is to just optimize them separately. So you will do hyperparameter optimization for one of the optimizers separately. If you have hyperparameters that are common to all of them, then it's worth looking into solutions that support conditional hyperparameters. And for this, I would say the best support is found in the SMAC 3 and Hyperupt, two other libraries for hyperparameter optimization. And finally, one type of the categorical dimension that I've seen often with the students is a discretized float, I would call it, or a discretized, categorical discrete numbers, let's say. So in this example, I give the learning rate, which is continuous, that is turned into categories. Right? So the student, for some reason, wanted to try specifically these values for the learning rate. I do not recommend doing this for two reasons. One is that it makes the optimization harder for the optimizer. If you have an algorithm that works well in continuous space, well, then you just turn this continuous hyperparameter into a categorical one. So it becomes very difficult for the algorithm optimize efficiently. And another reason is that you don't know what the best values are. It may be 0.05, not 0.1 or 0.01, and now you just miss out on those values. So I do not recommend to do this discretization here. And if you really want to have a finite precision, because you don't want to have numbers that looks random with infinite precision, you can use instead a precision argument. So in Orion, if you define the log uniform from the smallest value to the largest one, you can give a precision up to the number of decimals that you want. So then the algorithm is able to work into, say, in continuous space, but when they are evaluated, they are rounded to the level of precision that you want. So now choosing the algorithm. First, we need to choose the budget. So the budget is the number of trials. I don't think I defined these words already. Sorry about that. So when you do hyperparameter optimization, the entire process, I call it an experiment. And each set of hyperparameters that you try and that you execute, so each training, we call it a trial. And now choosing the budget means choosing the number of trials that you can afford, or you should afford if you want to have a good result. So if you have just one hyperparameter, here it will be x. Okay, it's fairly simple to see, what kind of budget you should have. You should have. If you have 5 trials, 5 different points equally spaced, you can see that you have a coarse coverage of the space. If you would have 10 points, then you would have fairly good coverage of the space. So with just one hyperparameter, you can infer that about 10 is good. But then if you move to 2 hyperparameters now, x and y, it scales exponentially, right? We have 5 times 5, so we have 25 points that coarsely covers the space. If you want to increase to 10, it increase quickly, so it becomes very expensive. And now if we go to 3 hyperparameters, just 5 by 5 by 5, it's 125 trials. It becomes a bit expensive now. You don't want to scale that way, right? I would say in general, a good starting point is to have at least 5 times the number of dimensions. So not scaling in the exponential, but just linear. But obviously that's just a starting point, because it's a bit more complicated than that, right? This is just a heuristic. Let's say this is your search space. Okay, so you have this axis here is the x2 is one hyperparameter, x1 is another hyperparameter, and then you have the z-axis, which is the objective. Okay, you want to minimize, and the color is in function of the objective as well. You can see that if you have a search space that looks like this, it's fairly simple to optimize. And if you have just 5 times the number of dimensions, so about 25 points, if you're random or if you're in a grid search, you're quite likely to have at least a few points that is in the blue region. Okay, so 5 times the number of dimensions would be good. But if you have a search space that looks like this, where it's really steep and it's a really small region that is optimal, then with just 5 times the number of dimensions, you're likely to just fall always on this plateau of a 0 objective and never find the optimal region. So now you would need a lot more than 5 times the number of dimensions. So that's why I'm saying 5 times the number of dimensions is a good starting point. And then you should look at your results and then decide whether you should run more trials or if it's good enough. And obviously, if you have a lot of resources, you don't need to make this stopping point and evaluate and continue on. But if you don't have a lot of resources, it's good to make this step and then decide if you continue on or not. So now, how do we choose the algorithm? There is no silver bullet. What I will say here is just a general rule of thumbs. In most of the time, I would say it applies well, but there's some corner cases that I do not cover that may make these rules not the most efficient one. So I'll go over 5 questions, and I will lay out as a kind of a decision tree to how you can pick the right algorithm to use. So first question is, how many dimensions, how many hyperparameters you want to optimize? If you have less than 3 hyperparameters, I don't think it is worth using a complex algorithm. You can just use grid search and random search, and that will be good enough. Above 2 hyperparameters, especially for grid search, it becomes inefficient. So here, this plot comes from a very famous paper of Bergstra and Benjo from 2012, where they explain why grid search is not a good algorithm if you have more than 2 hyperparameters. And just in 2 dimension, you can see here the green area is the how good a hyperparameter is. Okay, and you see that the region of optimality for this hyperparameter. So here is the different values of a hyperparameter, different values of another hyperparameter. You can see that the grid search is missing it. Right? You would need to have a more fine-grained grid search to find this region. Whereas for the same number of trials, grid search managed to find it, right? Because it's more, let's say, diffuse on each axis. All the points are distributed. Okay, so if you have more than 2 hyperparameters, forget about grid search. Yeah, but below 3 hyperparameters, grid search, random search, simple, and it's good enough. Next point, computation time per trial. So if training, running a trial takes less than a minute, then it's cheap enough that you can just brute force it, right? Typically, if it takes less than a minute, you should be able to afford to run 1,000 of them. So in this case, again, don't make it complicated. Just grid search will be more than enough. But then if it takes more than 5 minutes, and here the numbers, it's approximately, there's a gray zone also. It's not clear when exactly this shift is made, but if you have some trial that take, say, more than 5 minutes, then you should try to use more sophisticated algorithms. So third question is, do you have late learners? I'll first just give an idea of what the algorithms here are, and then I'll explain what the late learners here. So if you don't have late learners, which is still to be defined, you should use algorithms that are Hyperbend and ASHA. These, in a very simple explanation, are like a random search where you do a very aggressive early stop on the training of your models so that you make it more efficient. So just to give an example here, the blue curves are the learning curves of different models. Okay, so different set of hyperparameters. X-axis is the number of epochs, y-axis is the objective. So as the training goes, the objective is getting better and better. Here in this case, it's the lower the better. Yeah. And these algorithms, what they do is that they sample a lot of different set of hyperparameters. And then after a few epochs, they will stop about, let's say, 3/4 of the worst performing trials, set of hyperparameters, and they will let the rest continue. And then again, they will stop about 3/4 of the worst performing algorithms, and they will do again and again until the end. So you will have just a few trials. There will be just a few set of hyperparameters that will be trained until the end. But in the end, you will have tried a lot, like a large number of set of hyperparameters. But this is a bit dangerous in some case, because if you have a late learner, then you will stop a trial that seemed to be bad at the beginning, but would have been one of the best if you train it till the end. So this example here that I give is on the x-axis, again, is the epoch, y-axis is the objective, and this one is reversed, so the higher the better. Each line, again, is a training of a different model, okay? And from blue is the best one to red is the worst ones. And I just put in bright red here the best one. Okay, so it's the one at the top here. And what you can see, also it may be a bit difficult because the lines are too thin, is that there's a lot of good performing trials that are blue here that goes through the bad ones and then becomes the best ones, okay? And the red one here was too low to be able to train with Hyperbend. So this is an example where we were trying to debug or try to understand why in our experiments Hyperbend was systematically being outperformed by random search. Okay, so we had better results with random search than Hyperbend in these experiments. And when we trained about 1,000 models, we realized that that was the reason we had late learners. And in this case in particular, that was caused by the gamma hyperparameter. So when we were optimizing the gamma hyperparameter, the most efficient ones were causing this behavior, so late learners. So it's not always obvious in the beginning if you are in a setup where you might have late learners. So if you decide to optimize with Hyperbend, I would say be careful and make sure that you're not having inefficient results, because late learners. Now, if you know you have late learners, you should avoid the hyperbanded ASHA. And based on how many trials you have, so if you have many trials, or let's say you want to run less than 200, if you run less than 200, it is worth considering algorithms such as Bayesian optimization, DPE, which is a form of Bayesian optimization. I won't describe here the details of these algorithms. I'll just say that they're adaptive methods that more and more look into the most efficient regions while still exploring a bit around them. So I'll limit to this. If you want to know more about Bayesian optimization, I invite you to look at the great survey of Agnihotri and Batra. There's the full reference at the end of the slides if you want to look at it. It's a great survey. And so if you have more than 1,000 trials, well, there's two things. Bayesian optimization will become slow. It can take several minutes, more than 5 minutes, just to sample a new trial. So if you want to be fast, it may be a bad thing. But if all the dimensions are continuous, so fifth question, are all dimensions continuous? If they're all continuous, Bayesian optimization is such a great optimizer in a continuous space that it may still be worth using this algorithm, even if you have more than 1,000 trials. And if not, if you have discrete dimensions or categorical dimensions, Bayesian optimization can still be applied. And this is why here, this is not dependent on the type of dimensions. But at the scale of 1,000 trial, even if it can be used, it may become not so efficient with respect to a simple random search. The point here is that Bayesian optimization, it's an efficient algorithm, but what you will gain with it is speed of optimization. So you will find the best results faster than random search. But if you are in a case, for some reason, that you can afford running about 1,000 trials, if you just have a few hyperparameters, it's 5 hyperparameters, well, with 1,000 trials, it's starting to be brute force. It's starting to be like you're brute forcing the optimization. And in this case, the random search will reach as good results as Bayesian optimization. So if you are in this scenario, don't make it complicated for nothing, just use random search. So that's all for the decision tree, let's call it, for the decision of which algorithm to use. I would say in general, in deep learning, the most typical scenarios is either you don't have late learners and you can afford Hyperparameter and ASHA, which is great because typically deep learning takes a little more time to train. Or you cannot afford to have a lot of trials because it takes a long time to train, again, the deep learning models typically. And so you're better off using Bayesian optimization at TP. So I would say in general, this is the two algorithms that are the most typical ones for deep learning. Now, how to run hyperparameter optimization. I'll start with a few tips. So first tip is when you set up your experiment, be careful if you have a small validation set. It may be surprising, but if you have less than 1,000 samples and you have, let's say, 5 hyperparameters, it is quite likely with an algorithm like Bayesian optimization that you will overfit the validation set. So that means that you will select hyperparameters that are improving the objective on the validation set, but are not improving it on the test set. They're not generalizing. Okay? It's we often hear about overfitting on the training, but it's also possible to do it in the hyperparameter optimization. So be careful if you have not enough samples in the validation set. And in this case, if you have not that much samples, you should do cross-validation. Cross-validation for hyperparameter optimization, all it's done is that you do your cross-validation for a given set of hyperparameters. Okay, so let's say you have 5 folds, you train your model with the same set of hyperparameters on the 5 different folds, and then you average your performance and you return this to the hyperparameter algorithm, hyperparameter optimization algorithm as a single metric, and you will do the optimization on these average. Another point is that you should randomize your Cs within the cross-validation. And if you do not do cross-validation, so that you, for a given set of hyperparameters, you just train once, right, on your training validation set. And in this case, you should fix the seeds, okay? Because if you do not fix the seeds, when the algorithm is starting to converge on the, let's say, best region of hyperparameters, what would happen is that for a different set of hyperparameters that are let's say, equally good in terms of the objective, okay, now on average, the algorithm will start selecting these set of hyperparameters that were just by chance run with a seed that was giving a best performance, okay? And these seeds do not generalize across tasks, across runs, okay? So it's not good to optimize the seed. And so again, if you cross-validate, randomize the seeds within the cross-validation, but if you do not cross-validate, fix the seeds. You don't want to optimize the seeds. A common issue that I've seen with the students that made the optimization let's say a pain to execute is the handling of some failures. So make sure that you handle let's say out of memory errors, in particular if you're sharing GPUs with others and you know that you might have issues with the memory, or if you have a hyperparameters like the layer size that may cause out of memory. So be sure to catch this error. With Orion, we have a helper function, this client.interrupt trial, that will just interrupt this trial if this is an issue that is caused, for instance, because you're sharing the GPU, and it will try running it again on another worker. Or then if you have NAND, so maybe some of the hyperparameters cause a divergence issue in the optimization and you have NANDs, make sure to catch those. And with Orion, you can use this client.report bad trial that will just return a very bad objective to the algorithm so that it start avoiding this region of the search space that is causing that. And a last tip is about the time, because hyperparameterization takes a lot of time. So you want to optimize as much as you can the execution of the trial to make it short. So first of all, you should not let the bad trials continue. You should use early stopping. I've seen often people not use early stopping when they were using an algorithm like Hyperband because they were thinking that Hyperband is already doing the early stop. But this is a different kind of early stop. You can combine these together and that will be even more efficient. So make sure to use this early stopping so to avoid training too long a trial for nothing. Also, I already covered this a bit. If you have some hyperparameters that make the training take more time because it increases the computational complexity, like increasing the size of the layer, it's better in this case to limit training time in terms of wall clock time instead of number of epochs. This is not always possible if you're training a model for like 5 epochs. If you stop in terms of the training time, it may be an issue if some model was trained for 3 epochs or 5 epochs. You know, it makes a big difference, and there's a discretization of time in terms of the large epochs that takes a long time. But if you train for 120 epochs, this is not an issue. And finally, this is not specific to hyperparameterization, but I've seen it many times, and it's an important one. Make sure there's no bottlenecks in the data loaders. Sometimes it's a bit surprising to some of the students, but their experiments are training, let's say, 5 times slower than they could do because they have, let's say, just one worker that is feeding the data. I'm talking about PyTorch workers, for instance, that are feeding the data to the GPU, and makes it a lot slower. So make sure that you have an efficient pipeline to feed the GPU for the training of your model, because this can be very costly in terms of time. And if it takes five times slower to train your model, and you have 200 trials, and it's 5 times 200 trials the time it takes to train, it makes a big difference. All right, so now how do we run the hyperparameterization? This is an example with Orion. So let's say we have this simple function, Rosenbrock, that takes x as a hyperparameter and returns the objective. With Orion, what you would do is you import this working function. We define the search space. So x here is the hyperparameter, and we pass it. We assign it a prior that is uniformly distributed between 0 and 30. So this is the different values that will be tried. And then you just call work on the function, pass it the space. And for example, here we set max trials to 20. And now this will sequentially do the optimization and return the experiment. This is a very simple function. If you want to try something that runs quickly, you can do it sequentially locally. But most of the time you will be optimizing models that takes a long time to train, so you want to parallelize it. For this, you can use the build experiment function in Orion. So again, we define the space. In this case, we define a storage. So in previous example, we were using in-memory for the saving of the experiments, the results. Okay, now it's a database that is based on the file system. In this case, we have other storage. I will cover this later. So in this case, it's we call it a PickleDB file-based database, file system-based database. Okay, we pass this to the build experiment. So name of the experiment here, pass the space that we just defined above, the storage configuration. Now we have our experiment object, and we can just call work on with this experiment object. And so it will optimize this function, and we set the number of max trials here. If you just call this script here, again, it will be sequential. But the difference with the other script is that this part here, if you execute the same script many times, it will launch in the backend workers, different workers for each execution of the script that will synchronize together through the database. So to parallelize this hyperparameter optimization, you just execute the same script many times on, say, different machines. Different machines. As long as they share the same file system, you can parallelize this way. Otherwise, you can use a MongoDB, as I'll cover later on, in which case you can really distribute it even on different clusters. Okay, so that was a very simple example of how to run the hyperparameter optimization with Orion. Now we'll look at the visualization that are possible with Orion. So we add our experiment object. Remember, now we just call .plot.regret. It gives us a figure, fig.show, and this would open up in your browser if you were to execute this on your computer. This first example here is a regret curve call. So the x-axis is the different trials, so different set of hyperparameters that are being tried, okay, across time, and the y-axis is the objective. Okay. In this example, it was a TPE, the tree structured Parson estimator. It's a kind of Bayesian optimization. Okay, 5 first points are just randomly sampled, and then TPE really kicks in and starts trying to optimize by looking at the region that seems the most promising one. And you can see how it successfully do this by trying, this set of hyperparameters was better than the first one, and then goes on and optimize it until it goes to some optimal region here where it converge. So this plot, most importantly, it conveys how quickly the algorithm found the best hyperparameters. And one thing to be careful about is that if the algorithm converged here, because it converged doesn't mean that it found the best results. Okay, it might have converged in the local minima. So it really just tells you how quickly it converged. It doesn't tell you if it converged to the best values. Right? Another plot is the parallel coordinate plots. So this one conveys a dense overview in a multi-dimensional space. Each column is a different hyperparameter, okay? And each line is a trial, so a set of hyperparameters connecting at the corresponding values for each of the hyperparameter. And it's colored in function of the corresponding validation error rate in this case, so the objective. And you can see, like the small values for the learning rate were mostly very light, otherwise red. So this is how you can use this plot, for instance, to identify the optimal regions for different hyperparameters. And as you see here, like as I'm discussing, it's all moving around because this is very useful if you're in an interactive mode and you can move around with your cursor and just highlight some subsection of the space if you want to look, like just the trials that train until the end for 120 trials, or those that train until 30 epochs. This is an example where we use the hyperband. This is why we have different number of epochs. So it's good to identify the say trends of best and worst hyperparameter values. But to be very honest with you, I find this plot a bit difficult to read. So I'll show you 2 other type of visualization that I think are easier to intuitively understand and work with. So first one is a simple bar chart, which contains a lot of information, but in a very dense way. very compact way to say. It's called the local parameter importance. And what this measure is, given a set of trials, so let's say you train for 100 trials, okay? Given the set of 100 trials, what was the importance of the different hyperparameters in achieving this best result? So if you take the best set of hyperparameters, okay, and you change the learning rate, for instance, how much it will degrade the objective. And you see in this case that, for instance, learning rate, gamma, and the epoch. So again, this is an example with the hyperband. That's why the epoch is here. You see how much they affect the objective. And you can see that given the best set of trials, the best set of hyperparameters, if you change the momentum or if you change the weight decay, it does not have so much impact on the final result. So this is a very compact and easy to read visualization. It can be a bit misleading, however, because it depends on the set of trials that you've tried, right? So if you visualize this plot on a very small set of trials or a bad set of trials where you never found the best hyperparameters, it may not be very informative, or at least the information that it conveys is misleading. So you need to be careful with this plot. And now my favorite one, I would say, is the partial dependency. Right, so here we have on the different column, different hyperparameters, and different rows is the corresponding hyperparameter. So for example, here in this contour plot, you have the learning rate on the x-axis and the momentum on the y-axis. And the light region here is the region where it's optimal, where we have the best objective. And the dark blue is the worst one. And with this plot, you can easily see, for instance, what was the best region of the values for the hyperparameters. Oh yeah, on the diagonal here, it is the average value, average objective you would get for the different values of let's say, learning rate. So for different values of learning rate, if you randomize all the other hyperparameter, what is the average objective you would get? And you can easily see what is the optimal region for some of the hyperparameters. And I really like this type of visualization because, let's say you, as I was saying earlier, if you run for 5 times the number of dimensions, and then you visualize this plot, this parallel dependency plot, now you can see, okay, I'm wasting a lot of resources on these values of learning rate. Okay, so now I will continue this hyperparameterization, but I will narrow it down to this region instead, to make sure that all the trials I'm trying out are worth the time. And you can also see that some of the hyperparameters, so in this case the weight decay, are not really making any difference. And so if you have any trials to be sure that this is a reliable information, you can just prune it out and then continue the optimization with 3 hyperparameters instead. And this will help the optimizer to converge more efficiently. Oh yeah, and it may be difficult to visualize all the space if you have a lot of hyperparameters. So obviously there's a way to select a subset of hyperparameters to just the C2, let's say. Okay, so quickly, how to make efficient iteration in HPO with the experiment version control in Orion. So this is the feedback loop here, this 5th-step adjust design. So first of all, what is the experiment version control? You can think of it as a code version control, but at the level of the experiment for the hyperparameterization instead. So it detects any modification in the configuration of the experiment, configuration of the search space, the algorithm. It can also detect the code version if you're using Git. It can also detect if you're using the Python API. So the example so far was in Python, but there's a command line API. If you're using it, any difference in the command line call to run your hyperparameterization can be detected. And when there's such modification detected, instead of just running the same experiment and now corrupting, let's say, your results with trials that are not run exactly on the same code or not sampled exactly from the same algorithm, Orion will branch the experiment. So it will create a new experiment that we call the child experiment. Here it's represented with this little tree. So let's say we have this root experiment. We change a bit the search space. We expand it a bit. And now we'll have a child experiment that will be connected to the parent one. And it will have access to the trials of the parent. So when you do this optimization, it will be, as we call it, warm started. So there will be trials coming from the parent that can be used to train your algorithm, your optimization, hyperparameterization algorithm. And also you keep traceability with this. So when you make a modification, you know that all the trials in the child one were run with this modification and the previous trials were run with the previous version, right? So just to give a visual example here, let's say we add 4 different trials in the root. Now we branch because we expand the search space. And from this, now let's say we were using Bayesian optimization, it can already be fit on these 4 trials. And we can try 2 different ones that are being suggested based on the previous ones. And so this is good for 2 reasons. First one is that we have this warm starting mechanism that makes it more efficient. Instead of starting from scratch because you made a modification, you can reuse the prior information. And also it gives you traceability. So you know that these trials were run with this specific configuration, while these ones were run with the previous configuration. And also you can branch different trials. So you can, you can try running random search for 50 trials, and then you can try different algorithms based on the same warm starting to see how they behave differently. So that's for the experiment version control, how it works. Now, how to use it. I'm reusing here an example from previous slides. So we add this space, we build the experiment called random Rosenbrock, pass the space here, the storage, which was the PickleDB, so file system based. Then we do the optimization for 20 trials. And now if I call this fetch trials method, it will say that I have 20 trials in the experiment. Okay. Now I want to branch from it because I want to, let's say, narrow down the search space, and I want to change the algorithm, use one that is more efficient, let's say. So I reuse this build experiment function again. Now the experiment, I called it TP Rosenbrock. I changed the space a bit. So you see 20 instead of 30, same storage because we need to reuse the same database, obviously. Now I pass this TPE as an algorithm. So it'll be using the default configuration of the TPE. And on this new argument that we didn't use before, which is branching, and I say, okay, branch from the experiment random Rosenbrock. Now I have the TPE experiment. If I call fetch trials, it will say there is no new trials because this method here is just looking at the local child experiment. Now, if I call fetch trials with the argument with EVC3, true, EVC for experiment version control, now we'll see that there's 18 trials. 18, not 20, because we narrowed down the search space and some of the trials were out of bounds, so they were not compatible, and so they're not fetched. Okay, so now when we do this work on, oh, there was a mistake here. It should be TPE experiment work on. This TPE will be first fitted on the 18 trials that are coming from the parent, and then we'll continue on sampling new trials that will be saved in the child experiment, not in the parent one. So they keep being compartmented, partitioned, let's say. So that's it. This is how you use the experiment version control. And now if you use the visualization, as I shown before, let's say the partial dependencies, you can go iteratively, let's say run about the 20 trials, look if the search space was ill-designed, readjust, and then again, you branch from it, you run another batch of 20 trials, and you can go on like this to make it more efficient. So a quick word on Orion. At Mila, well, generally, as Yongang will just cover quickly based on our surveys, in academia, not a lot of researchers are using sophisticated hyperparameterization. Most of the people are using just grid search, random search. And so at Mila, we wanted to develop a framework that is very easy to use so that to encourage most of the students to do hyperparameterization. And so we build it to be easy to use. It is distributed and asynchronous. So there's no need to set up a master and workers. This gives better resiliency. It's easier to use. It's also implementation agnostic. Most of the people are working on Python. But in any case, if you're working on a different language, through the command line API, you can use Orion on any type of scripts. And also, if you want to define your search space in some configuration file, Orion is agnostic to any type of text-based configuration file. And so the search space can be defined in any of these. Quickly go over the workflow. So this is an example where we use the command line API, just Orion, Hunt, name of experiment, and here that would be the command line call that you use normally to do the optimization. If you do it once, you will have one worker, this bomb, and this worker will do the optimization sequentially. And now if you just run the same command many times on the same machine or different machines, you will have 2 times 2 worker, 3 worker, 4 workers. And now if we look at in a different view, what will happen is that each of the worker are working separately, okay? And in this loop, so now they look, is the experiment done? No. Is there a trial available in the database? No. If there's none, now they will enter this step here, which is the point where all the workers are synchronized together. So they update the algorithm based on the database that is common to all of the workers. And then they produce a trial that they add to the database. Okay, and all the workers are doing the same thing at this step here. So they are synchronized at this level. The algorithm is present in all of the workers, but it's like replicated across all of the workers. This is good because you can easily scale the amount of workers, and also you can easily lose workers without any problem because they can work on their own. They don't know how many workers there are, how many workers there is, and they can continue on. So this gives a better resiliency, and it's also easier to scale. So yeah, we have different storage backends. There's this in-memory version. There's a file system version, which students seems to like a lot, but it does not scale super well. So if you have more than say 200 trials, it will become slow a bit. And then you can use the MongoDB backend. We can easily scale above 1,000 trials. And we have a couple of algorithms, so grid search, random search, the hyperband and ASHA, as I covered. There's also this evolutionary ES, which is some kind of combination of an evolutionary algorithm with hyperband. There's GPE, the tree structured Parson estimator, and the Bayesian optimization, which is an external plugin wrapping scikit-optimize. So that's it for the quick overview. It's an open source, so you have a link here to documentation, source code. It's also easy to install from PyPy or Anaconda. I will now hand over to Youngang that will discuss a bit about the collaboration between Mila and IBM on Orion. Thank you.
I just want to check the time. Bill, I know it's at the end of our, can I have a few more minutes just to finish up?
Yeah, absolutely. Please go ahead.
Okay, great. And also in the meantime, I think Xavier can also answer other questions. I answer half of them. So in the next few minutes, I will talk about Mila and IBM collaboration. As I mentioned, we have been collaborating for the past year. And we have a press release announcement last December. Over there, you can also see the comment from Professor Yoshua Benjo from Mila. He was talking about the importance of HPO for energy efficient AI. Next chart. So as Xavier mentioned, HPO is very important, have a great impact to the final result. But also from the survey he did for NeurIPS and the ICRR conference, a majority of the user researcher still using manual approach and using a simple and inefficient method. The question is why? Next chart. There are pretty much 3 reasons. One is they don't trust the algorithm efficiency, maybe accuracy as well. The secondly, they feel that they don't have enough resources to do HPO hyperparameter optimization. The third one is about the usability. They feel that the entry bar is too high. Next chart. Those are the specific executive area that IBM and Mila have been working together. The first of all, we are working on new HPO algorithms. And in addition, we're also working on the benchmark to evaluate the HPO algorithms' performance and accuracy. This is mainly to address the trust issue of algorithm efficiency. Secondly, we are also working on warm start and the knowledge base. This is essentially leverage the prior knowledge to leverage the prior knowledge to fast track and accelerate the subsequent HPO process. It is to address the resource efficiency and HPO optimization. The third area is about the visualization and the dashboard. We are continuing improving the usability of HPO process. Next chart. We have been working on algorithms and also have contributed quite a few over the past year. Next chart. We are also working on the algorithm benchmark. The motivation for benchmark, they're twofold. One is to understand which search algorithm is good or suitable for which scenario or use case. The secondly is we want to create a tool to evaluate new search algorithms. To do that, we have a set of verification tasks, including synthetic function, the simulator to fast track the evaluation process and also allow user to utilize the real world task. And in addition, we also define several assessment scenarios, including time to result, average performance, the efficiency for parallel execution, and also the sensitivity for algorithms. Next chart. To use the benchmark is quite simple. You just include the module and create a definition of benchmarks. Over there, you can select which algorithm you want to compare, either existing algorithm or new algorithm. And then you define the task, evaluation task, and then define the assessment criteria. Next chart. HPO is very expensive. GPU is very expensive. V100 will cost more than $10,000. A DGX toolbox is equivalent to a sports car, like a Lamborghini. So this knowledge base and warm start is essentially to address the efficiency issue for HPO. We have some existing mechanism as Xavier explained using version control in Orion. We also have done some research work in the past to understand the similarity of a data set and then group the data set accordingly. And based on the similarity of a data set to determine which model and parameter to reuse. Right now, we are experimenting two approach. One is a recycling approach. Another one is a multitask approach. Our end goal is to enable the knowledge sharing across different experiments, not just from one user, but also from different users. And this is done through a knowledge base. Next chart. Xavier already mentioned we have quite a good set of visualization plot. And this is an area we continue working on that. Our goal is to provide an intuitive, concise information which correlates the trials and the objectives and the search space and improve the usability for user to use HPO. And there's more example notebooks in the link down below. And to use those plots is quite simple. It's very straightforward, just 2 lines of code. Next chart. Some of the HPO capability also available through IBM product, IBM Watson Machine Learning Accelerator, and the Cloud Pack for Data. There's tutorials and the blogs. There's a link available. And then next chart, the source code, the documentation, all are available online for Orion. Maybe we can have a few minutes for question and answer. Just
yes, great.
Yeah.
Great. Well, thanks a lot for the great presentations. Yeah, let's. I see there are quite a lot of questions in the Q&A. You can just go through them from the top to the bottom. And also reminder, we still have times. So if you have more questions, keep posting in the Q&A. And if you prefer to speak, to ask questions, feel free to raise your hand. We can unmute you. Yonggang, you can go ahead.
Yeah.
You can open up the Q&A.
Yeah, I open up the Q&A. I think the first question is how would the hyperparameter tuning in visual domain, such as style transfer? Xavier, you want to take this?
I guess the question may be more about what exactly metric should you use, because I don't see anything specific compared to another type of visual domain, like just image classification with respect to style transfer. But in the case of like GANs, for instance, GANs can be tricky to optimize, generative adversarial models, neural networks, because the training is so unstable that if you use something like Hyperband, it will quite likely not work very well. Otherwise, yeah.
Yeah, Alex, you can clarify. I just
yeah. So what I mean is I have it's not necessarily like a learning problem, but more like of an optimization problem that I want to do style transfer to, let's say, an image. And there are several hyperparameters to use, for example, which layer or whatever. But necessarily the loss does not indicate which looks best, because it's kind of like a visual domain and you have to visually check which looks best. And do you have any suggestions how to handle these cases where you cannot assign a number to the quality of the results, basically?
Well, difficult because it's kind of like the cookie experiment. I don't know if you're familiar with this. Maybe I can share it in the slides when I share the slides. At Google, they applied hyperparameter optimization on a cookie recipe. And so it was the same problem. You cannot just put out a number. This cookie is good, 8 on 10. So people had to eat the cookies, and then, there was some noise on if someone likes the cookie, who doesn't like the cookie, and then it's just a manual process at this point. So for the images, I don't know. I think the best for you would be to look at the scoring metrics for something like GANs and use this kind of function. But even then, it's not always clear if these way of measuring the quality of an image is a good one.
Okay.
So I'm afraid it's still it's still pretty much a research question. How do you measure this? How do you quantify this quality?
Yeah, that's what I thought. Thanks for your answer anyway.
The next question is about a specific chart. I think in your portion, Xavier. For the macrocombinate function.
Combinate function. Oh, I think you're talking about he's talking about the example of difficult function to optimize. That was the second one. I don't remember, to be honest. I just look at the different toy function that we often use for the optimizer, and I picked the one that was the hard one to optimize. Yeah. There's the question below. Okay. Okay, so sorry, things were moving around. Okay, so there's this question: what would be a good range to try on seeds? Based on our experience, the results are highly dependent on the seed stochastic algorithms. When fixing the seed, be cherry picking. Okay, I don't think there is a range for seeds, right? Because there's no, you cannot say one seed number one means this. It's stochastic. So I think the question would be, how many seeds should you try? And so yeah, there's a couple of questions at the same time. So okay, let's first answer: wouldn't fixing the seed be cherry picking? Not necessarily. If you fix the seed and then you do the optimization, for all of the trials, the same seed, you didn't cherry pick the seed. You just fix it in advance. Maybe you could have chosen another seed and then you would have better results, but then that would be cherry picking. Another thing is, if you fix the seed, it may be good to randomly fix the seed at the beginning, so that each time you do hyperparameter optimization, maybe you're using a different seed. But then again, this is tricky because maybe sometime you won't improve anything, but you just fall on the lucky seat. So the best thing to do, which is not something that we can do in practice often, is to just run it many times. And I'm talking about running many times the hyperparameter optimization. And obviously this is too expensive. So in case where it's too expensive, I think just fixing the seed is still the best solution. Which HPU should I use for time? Please suggest something. I must be honest, I am not familiar with time series analysis. I haven't worked with this very often. So if you're saying, so if HPU is apply on the time series, so it is dependent on sequential steps, there exists solution for Bayesian optimization on this. But out of the box, in most of the hyperparameter optimization libraries, you won't find these kind of Bayesian optimization. I think you can find them quite easily if you just Google Bayesian optimization time series analysis. But other than that, if you are optimizing the hyperparameters of an algorithm that is trained on time series analysis, then I don't think it makes a difference if it's time series or if it's another application in machine learning.
Maybe I can add to that. I think it's depending on which algorithm or model you're using. There are different approach. There's a sequence-based model, LSTM. Currently, there are also popular approach using temporal CNN. Maybe some of the language model can be applied using through a transformer. If you're using all those models, I think all the search algorithm that Xavier talk about should be all applicable.
Okay, first at the top, what are conditional hyperparameters? A conditional hyperparameter is a hyperparameter that you will only optimize if the value of another one is to a certain value. So if you are optimizing, let's say, what type of optimizer, like ADAM or SGD, but then you also want to optimize the beta 1, beta 2 hyperparameters of ADAM and learning rate of SGD, then these two, the beta 2 and beta 1 and the learning rate, they are conditional hyperparameters. They're conditioned. They will only be optimized if the hyperparameter, say, optimizer is equal to this type of hyperparameter. This is what we mean by the conditional hyperparameter.
Roughly how many lines of code in Orion?
Oh my God.
Do you remember?
I don't know. It's more than 20,000. I think if you look at the, you can look on GitHub the contributions, and you'll see how many lines have been contributed to it. Okay, is it more important to converge faster or converge to a relatively smaller objective value or higher accuracy? In which cases late learners are preferred? Okay, so the late learners are not at the level of the hyperparameter optimization, right? It's at the level of the optimization. It's within the black box that we're optimizing. When late learners are preferred, well, what I call a late learner is not just a learner that is slow, but it's a learner that will outperform, but it is slow at the beginning. Okay, so by definition, this is the kind of learner that you want, because by definition, it's the learners that will outperform the others. Okay, so I make a difference between just a slow learner and a late learner. Late learner is one that will outperform the others. So in which case is it preferred? Well, you know, if you are in a situation where there is late learners, you prefer them because by definition they're the best one. The important point when you're deciding what kind of hyperparameter optimization algorithm you're using is there late learners in your setup? And a good example of this is, for instance, if you're optimizing a VGG, any VGG on CIFAR-10, and you have a learning rate, schedule with steps, like at the 30 epochs you have the learning rate, at 60 epochs you have the learning rate. This one will not have late learners. And if you use a learning rate schedule, like an exponential learning rate schedule with gamma, this version will have the late learners. And then the question is, which version will perform better. In our experiments, it was the exponential learning rate schedule, but it may not always be the case. So you need to play around and see. Okay, quick answer. Are partial dependencies and LPI part of Orion or something else? Yes, they are in Orion. Can you recommend a good online course on this topic, on hypertransition particularly? I'm not aware of any that are particularly on this topic, but I will share the slides, and in the references, there's a couple of academic papers that maybe are not the best for this, but you can look at least the tutorial for Bayesian optimization and the AutoML book from Hutter et al., which are a good read for an introduction to the topic.
The next question is about does Orion automatically choose whether use a random algorithm or Bayesian based on the flowchart you presented earlier? No. The answer is no for now, but this is ongoing research area, also part of a collaboration between IBM and Mila as a part of this research for warm start knowledge base.
And so for the last question, is HPO on real-time data possible? That is changing periodically. Does Orion support that kind of stuff? Yes, it is possible. There exists an HPO algorithm called PBT, which is somehow doing this. So it's changing the hyperparameters during the training. PBT stands for population-based training. It's a very good algorithm for reinforcement learning in particular, where the learning rate schedule, well, a schedule for the different hyperparameters is important. We don't have it right now in Orion, but this is one of the algorithms that we want to include soon. That would be the first algorithm that works on real-time data in Orion. Oh, so I see there's a lot of in the chat as well.
I think most of the chat is already posted in the Q&A, right? Or some.
Okay. Oh yeah, I see.
Yeah, I also answer a number of questions. Right now it's in the answered area. There's one specific things I want to maybe reiterate a little bit. I can see there's a follow-on question. The question is about the latest GPU support subdivision of one GPU into multiple chunks. Does Orion support to run 8 trials simultaneously on one GPU? And does Orion have ability to run trials simultaneously on all the cores or on multiple cores of CPU? So this is aligned very well with our goal to make HPO efficient, high efficiency for HPO process. From IBM perspective, we have done a lot of work to optimize inference training on GPU, either one GPU or multiple GPU, and also do the GPU packing with intelligent scheduling. And this is also an area we plan to work together with Mila as well. There's opportunities to run multiple trials on the same GPU to have a better utilization for the GPU and also leverage multiple GPU across clusters. The answer for whether Orion currently supports the cluster, it does. Orion supports running Orion Hunt on one machine, but also you can run Orion on multiple machines and running either on a HPC cluster or a Kubernetes cluster. So it does